In this problem, we're presented with a data set for an RLC circuit, that's a resistor, inductor, capacitor circuit, and we're told it's connected to a 0.4 volt AC voltage. And just to clarify what that means, I'm talking about the peak voltage here, or the voltage amplitude. And what we've done in the experiment is vary the frequency that we're driving the circuit at, and we're measuring the current through the circuit. And we see immediately that there's a special point here where the current through the circuit is maximum. That happens at the resonant frequency for the circuit, and that looks like roughly 55 hertz. So in part A, we're asked to estimate the product of inductance and capacitance. In other words, the product LC. And all I'm doing here is relating this to the resonant frequency. We recall that the resonant frequency is given by 1 over 2 pi root LC, and we can just solve this for LC and plug in our approximate resonant frequency. So I multiply both sides by square root LC, and I divide by F naught, the resonant frequency. Then we square both sides to undo that square root. And finally, we plug in the resonant frequency that we approximated from our graph. And when I run the numbers on this, I get 8.37 times 10 to the negative 6. But what are the units on this number? Well, if I go back and look at my resonant frequency formula, I know that frequency is measured in hertz, which is 1 over seconds. And to get 1 over seconds to pop out on the right side of this equation, the product of L and C must have units of seconds squared. Now in part B, I want to find the total resistance R for the circuit. And the key concept here is to realize that the resonant frequency happens when the impedance of the circuit is minimized. Just a quick reminder of the impedance formula. And this is the generalization of resistance that we have to use in AC circuits. So the impedance is made of the ordinary resistance. That's what we're interested in this part. And then I have this difference between inductive and capacitive reactance that we're squaring. And at the resonant frequency, the capacitive and inductive reactance are equal to each other. That term vanishes, and I get my minimum impedance for the circuit, and therefore the maximum current. So what I'm saying is that at the resonant frequency, the impedance reduces to just the square root of R squared, or just R, the ordinary resistance. So when we apply Ohm's law to this thing at the resonant frequency, I'm going to write I equals V over Z. That's just the generalization of V over R. This reduces to V over R itself because we're at the resonant frequency. And then I can solve for R, and that's just V over I. We were applying a voltage amplitude of 0.4 volts. And when we do that, we see a current amplitude of 7 milliamps. So we plug that in. 7 milliamps is 0.007 amps. And when I run the numbers on this to 3 significant digits, I get 57.1 ohms, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.